Welcome students. We want to discuss about primality tests. So question is, given an integer n, given positive integer n, check if n is prime. So to answer this question, well, there are various methods to do that. First method, which is the trial and error method. Take all integers p, or let's use another symbol a, such that a is less than equal to square root of n, greater than 2, equal to 2, and check if a divides n. Yeah. If no such a exists, then we can declare, then we have that a is a, sorry, then n is a prime. Because if there is any factor, there is at least one factor which is less than square root of n, less than or equal to square root of n. Second is the Wilson's theorem. That is, if n minus 1 factorial is equal to minus 1 mod n, then n is prime. Third, we are hoping to see if we can use Fermat's theorem. So recall, Fermat's theorem tells you if n is prime, then we have b to the power n is congruent to b mod, right? So clearly, if a number doesn't satisfy us, if there is a b such that b to the n is not congruent to b mod n, then we can say right away that that number n is composite. So then the question is, what if some number satisfies the Fermat's little theorem? Does it still mean that it's prime? And the answer is no. So example, let's take n equals to 341, which is same as 11 times 31. So we can see that 2 to the power 10 is congruent to 1 mod 11, and 2 to the power 2 to the power 30 is congruent to 1 mod 31. And if we apply Chinese remainder theorem or otherwise, you can see that this means 2 to the power 10 times 30 . So we have 2 to the power. So therefore we get 3 to the power. This implies 2 to the power n minus 1. So what is n minus 1 here? 340. So 2 to the power 340, which is same as 3 to the power 10, the whole power 34, is congruent to 1 mod 11. And we get 2 to the power so we have 2 to the power 30. So the remainder is, so when you divide it by 30, so you have 2 to the power 10, and so 2 to the power 340 is 2 to the power 30 times 11 times 2 to the power 10, and that can be seen to be congruent to 1 mod 11 as well. So this implies 2 to the power 340 is congruent to 1 mod multiples of this, which is 341. So we can observe here that this satisfies the Fermat's little theorem, right? Because n minus 1 is 340, but we know that n is not a prime. So such an n would be called pseudo-prime to the base b. So 341 is a pseudo-prime to the base 2. Okay, so let's look at the definition again. So let b be a positive integer. If n is a composite positive integer such that b to the power n minus 1 is congruent to 1 mod n, then we call n to be pseudo-prime base b, or we can also call them as Fermat pseudo-prime. So then one may ask the question, does it happens occasionally or does it happens often? So we'll prove that there are infinitely many pseudo-primes to a base, at least let's prove it for base 2. Yeah. So for that, we'll need the following result. So if d and n are positive integers and d divides n, then 2 to the power d minus 1 divides 2 to the power n minus 1. So d divides n, this implies there exists k, and k is positive, right? Because d and n are positive, such that d equals to kn. Sorry, kn equals to d. So then we have 2 to the power n minus 1 can be written as 2 to the power k n minus 1, sorry, k. So d divides n means what? There exists k such that kd equals to n, right? So here we have kd, and now this can be written as 2 to the power k, or 2 to the power d, the whole power k minus 1. And the factorization of this goes as follows. So 2 to the power d minus 1, 2 to the power d to the power k minus 1, plus 2 to the power d k minus 2, dot, 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 2 to the d plus 1. Yeah, I'm using the following expansion here. The expansion is x to the n minus 1 is x minus 1 times x to the power n minus 1 plus x to the power n minus 2, dot, 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 plus x plus 1. Bracket close. So from here we can see that 2 to the power n minus 1 has this factor. Therefore 2 to the power d minus 1 divides 2 to the power n minus 1. Okay. So let's see. So now we can prove that there are infinitely many pseudo-primes to the base 2. All right. There are infinitely many pseudo-primes based other primes as well, but nevertheless, there are infinitely many primes to any given base. Although it's hard to find them for the other bases, but nevertheless, there are infinitely many. So let's prove this. So we have already produced one pseudo-prime to the base 2, right? So we start with the following. Let n be a pseudo-prime. So we have a constructive proof of it. will construct recursively pseudo-primes. So let n be a pseudo-prime to base 2. Claim that m equals to 2 to the power n minus 1 is also n. And of course, we are looking for odd pseudo-primes. So also an odd pseudo-prime to base 2. So to prove this, let n be a pseudo-prime. So we start with nb is a pseudo-prime. So therefore, n is composite. So proof, since n is a pseudo-prime, this implies 1, n equals to dt. Since n is a composite number, since n is composite. And secondly, 2 to the power n minus 1 is congruent to 1 mod n. Yeah, and here, since we are saying it's composite, we have 1 is, so your d is basically between n and 1. All right, strictly. So now, first of all, we'll show that m is, which is 2 to the power m. So here has to be 2 to the power minus 1. First, we'll show that 2 to the power n minus 1 is also composite. And then, so how will you show that it's composite? So note that 2 to the power d minus 1 divides 2 to the power n minus 1 if m is composite, right? So 2 to the power d minus 1 divides 2 to the power n minus 1 whenever d divides. So your m is this. We wrote m equals to nd, right? So we wrote n equals to nd, and we have the result from the here that if d divides n, 2 to the power d minus 1 divides 2 to the power n minus 1. So in this case, we get that since d divides n, 2 to the power d minus 1 divides 2 to the power n minus 1. This means that 2 to the power d minus 1 divides m. And note that 2 to the power d minus 1 is less than 2 to the power n minus 1, right? Because a strict divisor here. So therefore we get, so therefore m, this implies that m is composite. Now the next part we want to prove is that it's a pseudo-prime. So for that we need to compute 2 to the power m minus 1. So what is 2 to the power m minus 1? This is going to be 2 to the power 2n minus 1 minus 1. This is going to be 2 to the power n, 2 to the power n minus 2. And we are looking at this. So note that we have 2 to the power n minus 1 was congruent to, so since n was pseudo prime, we had 2 to the power n minus 1 is congruent to 1 mod n, or 2 to the power n was congruent to 2 mod n. So we got, from here we can get that 2 to the power n minus 2 is equal to 0 mod n, or it's some k times n, yeah, where some k is some positive integer. So this will become 2 to the power Kn. So then it follows that since we get therefore m, which is your 2 to the power n minus 1, divides 2 to the power k n minus 1, which is same as your 2 to the power from here, which is same as 2 to the power m minus 1 minus 1. So this implies that 2 to the power m minus 1 is congruent to 0 mod m because m divides it, or in other words, we get 2 to the power m minus 1 is congruent to 1 mod m. That is m is a pseudo prime base 2. Okay, and then this process can recursively go on and you construct all the pseudo primes. So now, there are numbers, composite numbers. So, well, this number here, if you go back, 341 was a pseudo-prime base 2, but it may not be pseudo-prime based other number, right? For example, we get 3 to the power, say, let's say 7 to the power 340 and check whether it's congruent to 1 mod 341. Yeah, so that can be checked in the following way. You can see that 7 to the power 3 is equal to 343, which is congruent to 2 mod 341, right? And we have 2 to the power 10 is congruent to 1024, which is congruent to, again, when you divide by 341 times 3, you get 1023. So it's going to be 1 mod 341. So therefore, we get, this implies 7 to the power 340 is equal to, so 7 3, so 7 cube, the whole power 113 times 7, which is 2 to the power 113 times 7. This is going to be 8 times 7, which is 56. That is not congruent to 1 mod 341. So the idea is that there is so 341 is a pseudo-prime. So 341 is a pseudo-prime base 2, but it's not a pseudo-prime base 7. So of course, then when you check with these two things, these two prime numbers, or sorry, these two bases, B as 2 and B is 7, you can see that, well, it doesn't pass this, so it's not a prime. However, there are some composite number that satisfy b to the power n minus 1 congruent to 1 mod n for all positive integers b such that b and n are 1. So such numbers are called Carmichael numbers or absolute pseudo-primes. So no matter what b is, as long as b and n are relatively co-prime, n passes the pseudo-prime test. So let's look at an example first. So example of a Carmichael number is the following. So consider 561 equals to n. So which is same as 3 times 11 times 17. Now let's take any B which is co-prime with 561. We want to show that this passes, B passes so 561 passes the test, or 561 is a pseudo-prime to this base B, where B is any base which is co-prime to 561. So to see that, notice the following. We have B. So since B and 561 is co-prime, it is co-prime with every prime factors of 561. So we get this. Now, if you use Fermat's theorem for each one of them, Fermat's little theorem, we get B square is congruent to 1 mod 3. B10 is congruent to 1 mod 11. And B17, so B16 is congruent to 1 mod 17. Now notice that we want to find out B to the power n minus 1. So notice that this is same as saying B to the power. So B to the power 560 is equal, congruent to B square, the whole power 280 is congruent to 1 mod 3. B 560, which can be seen as a factor of 10 as well, sorry, multiple of 10, is also congruent to 1 mod 11. And not only that, B16, B560 is also equal to B of 16 to the power 35, is also congruent to 1 mod 17. So if you combine all of these, you get B to the power 60 is congruent to 1 mod multiple of 3, 5, multiple of 3, 11, and 17. So we get 561. So we get that B is any number which is relatively prime to 561. Then we have that B to the power 560 is congruent to 1 mod 561. So such a number would be called Carmichael numbers or absolute pseudo-prime. So 561 is an absolute pseudo-prime. Prime or Carmichael number. So you see our hope. So earlier the hope was that even the number may be pseudo-prime, I may check with different base, and as we did in case of 341, and we found out that it did not satisfy the pseudo-prime with base as 7. But then there are numbers like these which basically are absolute pseudo-primes, that irrespective of the base, they are pseudo-primes. So seems like this method is not robust enough to find out whether the given number is prime. All right, it is easy to use them to find whether a number is not prime when it quickly fails the test. Okay, so seems like so if you look at Carmichael numbers, there is a very interesting pattern. The interesting pattern is you saw that here 2 divides 560, or in other words, your prime q, which was a factor here, q minus 1 divides n minus 1. So this is what is needed for Carmichael numbers. So here, or at least this is the case, in this case, we get a Carmichael number. So suppose n is q1, q2, qk, product of these primes, and qj's are distinct primes, that qj minus 1 divides n minus 1 for all j and k greater than 2. We need more than 2 primes. Then n is a Carmichael number. So let's see the proof of this. So proof, So let B be any base. So we are basically going to formalize this example into the theorem. So let B be any positive integer with B and N relatively prime. This means what? This means B and Qj are coprime for all j from 1 to k. This implies by Fermat's little theorem, b to the power qj minus 1 is congruent to 1 mod qj. Now note that qj minus 1 divides n minus 1 implies there exists ki, again ki positive because both of these are positive, such that qj minus 1 times ki is equal to n minus 1. So take star, raise star to power ki, we get b to the power qj minus 1, the whole power ki is congruent to 1 to the power ki, which is same as congruent to 1 mod qj. Or in other words, we have b to the power n minus 1 is congruent to 1 mod qj. Now, if you combine all for this for all qj, you will get, therefore, we get b to the power n minus 1 is congruent to 1 mod q1, q2, qk, or b to the power n minus 1 is congruent to 1 mod n. So therefore, you get a Carmichael number when qj minus 1 divides n minus 1. All right, so Carmichael number kills the hope of using this to decide the primality of a number n, positive integer n. So for now, then we'll move on to the next test. However, recall, we can try to salvage a little bit of this in the following way. If n is a prime, then x square equals to 1 mod n or congruent to 1 mod n has only solutions as x is congruent to plus or minus 1 mod n. Yeah. So in case we have a number which passes the Fermat's test, which is a to the power n minus 1 congruent equal to or congruent to 1 mod n, then we should check. So take x equals to a to the power n minus 1 divided by 2. Well, note that we are interested in only odd numbers here, right? Because for 2, we already know there's only one even prime, which is 2. But if n is odd, then you can basically look at n minus 1 divided by 2 and see what happens. So we have already seen that 561 is a Carmichael number. So 561, so clearly we have 561. So 5 to the power 561. So 560 is going to be congruent to 1 mod 561, right? Why is that? Because we proved 561 is a Carmichael number. So no matter what your base B is, as long as it is co-prime with 561, which your 5 is co-prime to 561, we'll get this. Now notice the following. So we will check. So we'll use this, that x is a to the power n minus 1 divided by 2. So let's see what is 5 to the power n minus 1 divided by 2, which is going to be 560 divided by 2, which is congruent to 5 to the power 1, sorry, 5 to the power 2 8t, and that can be seen as by computation. You can see that that's going to be 67 mod 561, right? So which is not plus or minus 1 mod n. So therefore here we are, 561 is composite. So essentially this did not work, but because of the Carmichael number, but now we have a slightly different variation of it. We know that even if we get x squared congruent to 1 mod n, and if n is prime, then x has to be plus or minus 1 mod n. Okay. So, however, there are some numbers which also pass this test. So you can check that 1729 will pass this enhanced test of primality as well. Yeah, that you will see that it will still be plus or minus 1 mod n. So let's check it. So we have 5 to the power 1729 minus 1 divided by 2. Let's check this. So this is going to be 5 to the power 1728 864, and that can be checked that it is 1 mod 1729. So this doesn't satisfy it. So what if we iterate this process? So what do I mean by that? What if we continue halving the exponents until we reach a number besides 1? If it is anything but minus 1, then n must be composite, right? So let's check this. So formally, we have if 2 to the power s is the largest power of 2 which divides n minus 1, then we have n minus 1 equals to 2 to the power s. So we go halving how many times? We can halve all the way until the 2 to the power s becomes 0. Or sorry, 2 to the power s becomes 1, or that means s becomes 0. So we'll basically half it as 2 to the power s minus 1t, a is 2 to the power s minus 1 dot 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 a to the power t. And then we check until then and see what do we get out of that. So here, so if n is greater than 2 and n minus 1 is 2 to the power s t, where s is a non-negative integer and t is a odd positive integer, we say that n passes the Miller's test. So this test is called Miller's test if you iterate it over and over again. Then what happens? Then either b to the t is congruent to 1 mod n, or when you're halving it, b to the power jt is congruent to minus 1 mod n for some j between 0 and s minus 1. Then we say that this passes the Miller's test. So this test is called Miller's test. Okay. However, again, the above test is not robust. But for example, we have n equals to 240, so 2047, which is 23 times 89. Now you can clearly see that 2 to the power 246 is congruent to 1 mod 247. The reason is 2 to the power 11 is 248, which is 1 mod 247. So you raise 2046, 2 to the power 2046 is congruent to 2 to the power 11, the whole power 186, but 2 to the power 11 is 1, so 1 to the power 86, which is going to be this. So it is a pseudo-prime. So n is a pseudo-prime. Not only that, continue the halving process. So we have 2 to the power 40 by 2 is same as 2 to the power 408 to the power 93. That is congruent to 1 mod 247. So it is not, it passes the Miller's test for base 2, but it is what? It is a pseudo-prime still. Okay. So then the question is, well, shall we discard this idea completely? Or basically, what if we check for sufficiently enough bases that the given number passes the Miller's test or not? Okay. So we want to show that if n is a prime and b the positive integer such that n does not divide b, then n passes the Miller test base b. So how do we go about it? So first of all, if you look at n minus 1, that is going to be 2 to the power s t, where s is a non-negative integer, right? So it belongs to z plus union 0. That's a short way of saying it's a non-negative integer, and t is an odd prime. Now consider xk to be, now we are going to half it, so b to the power n minus 1 divided by 2 to the power k. Of course, we can only half until s, so this is going to be b to the power 2 b to the power 2 s minus k times t. So therefore, we cannot go much bigger than k is 0, 1, 2, dot, 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 s. Yeah. Now, Fermat's theorem tells us, since n is prime, Fermat's theorem tells us that x1 square is congruent to b to the power n minus 1 divided by 2 the whole square, which is b to the power n minus 1 congruent to 1 mod n. Yeah, this last part is because of the Fermat's little theorem. Sorry, not last theorem, Fermat's little theorem. Last theorem is kind of out of our league at the moment. So now, since n is prime, we have x1 is congruent to minus 1 mod n, or x1 is congruent to 1 mod. So either one of this happens, all right? Yeah. Now, if x1 is congruent to 1 mod n, then we have x2 square is equal to x1 is 1 mod n, right? Because x2, that's how our definition is, right? x2 square is going to be multiplying by another factor of 2. So this is because of our definition here. X2 square is x1, x3 square is x2, and so on and so forth. Okay, so let me write that down in case. So x1 is x2 square, x3 square is x2, and so on and so forth until it is meaningful. So we get the following. So we have found out that either, so x2 square is this, and x2 square is congruent to 1 mod n. This implies again x2 is either 1 or minus 1 mod n, right? Either it's 1 mod n or it's minus 1 mod n. So continuing this process, so in general, continuing this process, so we have found that we have x0 congruent to x1 congruent to x2 congruent to dot 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 xk congruent to 1 mod n, or we have, or we have the following now. We have that either x for all k, either xk is congruent to 1 mod n, or xk is congruent to -1 mod n. Yeah, for some k. So rather we should say the following form. So for we have found out the following. So either we have xk or xs is congruent to 1 mod n. So this chain repeats for some s. So either this chain repeats or we get xk is congruent to -1 mod n. So therefore this passes the Miller's test. Okay, so let's have another look at Miller's test. So what does Miller's test tells us? That it passes the Miller test if either we have b to the power t is congruent to 1, or b to the power 2 jt is congruent to -1 mod n for some j in between here. So that is so we continue the halving process until either we stop at -1 mod n for some power, or we keep on going all the way until x to the power, in this case, uh, b to the power t, and get 1 mod n. Okay, so that's the idea. So now further discussion. So if n is composite and passes the Miller test for the base b, then we say strong pseudo-prime to the base b. Now the question is, how many such pseudo-primes exist? There are infinitely many such pseudo-primes to the base 2. In fact, to every base. There's nothing special about it, b. So then, is there any hope for this method of primality? And the answer is yes. But we have a probabilistic primality algorithm, which is called Rabin's test, which is also sometimes called as Miller-Rabin test. So what you do is the following. So suppose n is a positive integer. You pick k different integers less than n and perform Miller's test for each n. So for this n for each of these bases. And if n is composite, still remains a composite, the probability of that happening is 1 over 4 to the power k. So this Rabin's test is the probabilistic algorithm. The latest algorithm for primality is called AKS, Agarwal, Kayal, and Saxena. So these are classes of primality test. So the first algorithm was discovered, or invented by Agarwal, who was the professor for Kayal and Saxena. This was their undergraduate BTech project, and this was done in 2002. And it relies on the following, that n is a prime, then we get x to the power n is congruent to x to the n plus a to the n, which is x to the n plus a mod n. You're taking a and n to be. So it is what loosely based on. So we are going mod n. Yeah. So based on our freshman stream. So thank you for your attention.